So remember, we said that a strong acid is one that dissociates or breaks apart completely in water. Now, when we talk about how strong an acid is, there are several factors that will actually affect acid strength. The first is going to be the strength of the bond. If an acid is going to break apart completely, then I have to put in energy to break apart the bond. The stronger the bond, the weaker the acid. The reason is I have to put in more energy to break that bond. Okay? So a stronger bond is going to have a weaker acid. A weaker bond is going to have a stronger acid. The second factor that's going to affect acid strength will be polarity. Now, when we talk about polarity, remember, fluorine was the most polar. So fluorine is going to have most of the electrons going towards the fluorine. Now, when we look at this, you would expect the hydrogen ion to be able to break off really easy because it's going to be very, very stable to have an F- ion. However, hydrofluoric acid is not a strong acid. Now, the reason that this is because strength of bond plays a bigger effect on acid strength than polarity. Now, when we look at HF, HCl, HBr, and HI, as we go this way, it becomes least polar, but I is also the biggest atom. It has the biggest radius. Now, because it has the biggest radius, that hydrogen ion is really far away from the iodine nucleus, not a big pole, and so this can break off a lot easier. Fluorine is going to be the smallest radius, so it's going to hold on to that hydrogen atom a lot tighter. So polarity affects strength, but bond strength plays a bigger role. Okay? So another factor that affects it is the number of oxygen atoms that are attached to the central atom. So if we look at these different acids, perchloric acid, chloric acid, chlorous acid, and hypochlorous acid, this one is going to be the strongest. And here's why. If we look over at our tiny picture, this H, my acidic H, is actually an oxy acid. It's always attached to a hydrogen, the hydrogen's always attached to an oxygen. The oxygen is really electronegative. It wants those electrons. However, this oxygen is attached to the Cl, which is attached to other oxygens, which are also electronegative. The more electronegative atoms I have attached to my central atom, the more pull there is on those electrons, the less this is going to have electrons, and so it's going to be pulled here as well, and it's going to be easier for this hydrogen to break off. Okay? So another factor that affects acid strength is going to be attraction for a pair of electrons. Now, what that means is I'm going to look at the charge of a metal ion. Okay? The bigger the charge, the stronger my acid. Al is a 3+, very, very positive, which means the electrons are going to be drawn to this very, very positive substance. Because I have a lot of electrons being pulled away, it's going to affect my acid strength. Okay? Now, Oxyacids get confusing. And the reason oxyacids get confusing is because we can have an OH on them. So they look like they should be a base, but oxyacids are actually an acid. So when we have an OH, how can we tell if it's going to be an acid or if it's going to be a base? Now, if I have a covalent oxide, remember, I've got two nonmetals that are going to be sharing electrons. So sulfur's a nonmetal, oxygen's a nonmetal. They're going to share those electrons in a covalent bond. If it dissolves in water, what's going to happen is it's actually going to behave as an acid. Okay? If we look, H2SO3, sulfurous acid, carbon dioxide becomes H2CO3, carbonic acid, NO3 becomes nitric acid. So when it dissolves in water, it actually becomes an acid. Okay? Now, this one's kind of important. Whenever you have a carbonated beverage, so soda or anything with the bubbles and fizz, it's going to be slightly acidic, even if nothing else is added, because CO2 forms an acid in water. Okay? Now, if I have something that's ionic bonded with oxygen, remember, ionic is a metal plus a nonmetal. In this case, they don't share electrons. The metal loses electrons to form a positive cation. The nonmetal gains electrons to form a negative anion. What's going to happen is when this metal and nonmetal dissolve in water, my metal is going to partner up with the OH to form a base. Okay? So if I have something covalently bonded dissolving in water, it becomes an acid. If I have something ionic dissolving in water, it becomes a base. Okay? Now, so far, we've talked about Arrhenius acids. We said an Arrhenius acid is something with a hydrogen ion. We talked about a Bronsted-Lowry acid. We said a Bronsted-Lowry acid was going to be a hydrogen ion donor. Now we've got this new model. We've got a Lewis acid. Now what a Lewis acid is it's going to be something that can accept electrons. And this is, sorry, that should just be an electron. This is going to be different because it doesn't necessarily have to have an H anymore at all. It's just going to be able to pick up extra electrons. That's it. Now a Lewis base in this case is going to be an electron donor. So Lewis, and the way I remember it, Lewis has an E for electrons. So a Lewis base is going to donate those electrons, which means it usually has a lone pair. Okay? So this table talks about our different types. It's really important that you know the difference. Okay? Because sometimes they'll say which of these is an Arrhenius acid but not a Lewis acid, or which is Bronsted-Lowry but not Arrhenius, or something like this. Okay? So here's the way this works. This H plus is a Lewis acid because it is going to accept electrons, or a lone pair, from my Lewis base. My base donates electrons to this H plus, and it forms water. In this case, this H plus could be an Arrhenius acid because it's got H pluses. It could be a Bronsted-Lowry acid because it's donating an H+. It can also be a Lewis acid because it is accepting electrons. Same thing with my base. My base has an OH minus, so it's an Arrhenius base. It is accepting H pluses, so it is a Bronsted-Lowry base, and it's donating electrons, so it's a Lewis base. So in this case, this example is all three. Now ammonia is a little bit different, okay? In this case, I've got H+, here's my lone pair. So nitrogen in ammonia is going to donate the electrons to H+. Since this is accepting electrons, it's a Lewis base. Since this is donating, Lewis acid. Since this is donating electrons, it's a Lewis base. This is going to be an Arrhenius acid because it has an H+. It's going to be a Bronsted-Lowry acid because it's donating an H+. Now this base, on the other hand, if I look, it does not produce OHs. There's no OH anywhere here. So this is not an Arrhenius base. It does accept H pluses, so it is a Bronsted-Lowry base. So in this case, this is just Bronsted-Lowry and Lewis, okay? If I look at my third example, here we've got something that's a little different. Now, boron trifluoride was an example that we looked at that was an exception to the octet. Boron does not have 8 valence electrons in this stable atom. It only has 6. But because it only has 6, if ammonia comes along, it can donate these spare electrons to boron. Okay? So in this case, this is acting as a Lewis acid because it is accepting electrons. This is acting as a Lewis base because it is donating protons. If I look at the other categories, though, this does not produce H pluses. It is not an Arrhenius acid. It is not an H plus donor. It is not a Bronsted-Lowry acid. The only category it fits is a Lewis acid because it is accepting electrons. Okay? So make sure you can identify whether something based on the table, without the table, but you need to know these definitions, but make sure you can identify whether it is Arrhenius, Bronsted-Lowry, Lewis, all of them, some of them, but how it fits in.